Hello everyone, my name is Pat Jardine and I'm a master's student at Carleton University, supervised by Chris Byrne. This presentation will be discussing field experiments conducted last winter for the purpose of investigating snowpack compaction as a method of preserving permafrost beside highway embankments. The results of the experiments will form the basis of my master's thesis. The warming influence of snow on ground temperatures has been well established. It occurs because snow is an excellent thermal insulator, causing it to limit heat flow out of the ground. In 2019, a study conducted by Emma Stockton and others on the Dempster Highway found that ground temperatures were consistently highest at the embankment toe when compared to undisturbed ground and the highway centerline. This is because deep snowbanks typically accumulate along the sides of the embankment due to wind and road clearance. This is shown in the images on the left, taken at my field site on the Dempster Highway on June 2nd and December 1st. The diagram on the right was created by Guy Doré to illustrate how this warming influence may cause permafrost to degrade and threaten road stability. Once a road with standard embankment design has been constructed, in image B, the permafrost beneath the center line, where snow is cleared, remains stable and may actually degrade into the embankment. During the winter, when snow accumulates along the sides, the permafrost underneath begins to degrade due to the increased ground temperatures. Over time, as this cycle repeats, the active layer along the edge of the embankment deepens, and water from snowmelt and thawing permafrost may introduce further warming into the system, creating a positive feedback loop. The differential settlement caused by this process may result in shoulder rotation and longitudinal cracking on the road surface. Snowpack compaction may reduce ground temperatures by increasing the thermal conductivity of the snowpack, allowing heat to flow out of the ground more easily. This is because compaction removes air from the snow, and air has a thermal conductivity that is very low. Compaction was one of a variety of snow management scenarios simulated by Chris Byrne and Brendan O'Neill in a study in 2017. This figure was taken from their study and shows compaction to 400 kilograms per cubic meter under their M6 scenario in a tall shrub tundra environment, represented by TST2. While 400 kilograms per cubic meter is beyond what is being tested in my study, the result suggests that snowpack compaction may significantly reduce ground temperatures, even in a relatively short period of time. My project will continue this research by testing the effectiveness of this technique in the field. The experiments for my project took place at 5 field sites throughout central Yukon, indicated here by yellow triangles. The purpose of testing compaction at multiple sites was to see whether varying local conditions may influence the results. One of my field sites was located in the Blackstone Uplands, near kilometer 96 of the Dempster Highway. This was an alpine tundra environment, where high winds caused the snow to become hard and dense. The other 4 field sites were located near the village of Na-Cho, in a boreal forest environment. This meant that wind speeds were lower due to the extensive tree cover, causing the snow to be lighter. Aside from wind conditions, the topography, vegetation, and frequency of road clearance also varied between sites. These images show the 4 field sites near Na-Cho. The Stewart River site was located on Yukon Highway 11, the Silver Trail, leading into Na-Cho from the Klondike Highway. The Halfway Lake site was also located on the Silver Trail, but on a less heavily trafficked section north of Na-Cho, leading towards Keno City. Sites C and D were located on South McWeston Road, a road coming off Silver Trail which experiences less traffic and road clearance. I was originally scheduled to arrive in Yukon before the winter. However, I was delayed due to COVID-19 travel restrictions. This meant that topography, drainage, and vegetation conditions were difficult to assess during site selection, and temperature loggers had to be placed on the ground surface rather than buried, as the ground was already frozen. Once the sites were selected, adjacent 50-meter by 5-meter plots were delineated beside the road using wooden stakes. The sites near Na-Cho each had 2 plots, one of which was to remain undisturbed, while the other was compacted monthly. The Dempster Highway site had 10 adjacent plots, which alternated between being undisturbed and being compacted with varying timing and frequency. The project was conducted within the traditional territory of the Na-Cho Nyak First Nation. Their land guardians, shown in this image, compacted the snow using snow machines. They were instructed to drive over the snow repeatedly until subsequent runs no longer made any visible difference in snow depth. Along with ground surface temperatures, snow properties at each plot were measured monthly by digging snow pits. This is a before and after image of snowpack compaction at one of the Dempster Highway plots on January 8, 2021. Of the 5 test plots at this site, one was compacted monthly, one bi-monthly, one during the first 3 months, one during the last 3 months, and finally, one was compacted only once in the middle of the study period. This diagram shows how average snow depth, taken near the center of the plot every 10 meters, developed at the monthly compaction plot compared to the adjacent undisturbed plot. The rate of snow buildup was significantly lower at the compacted plot, and the difference between the two increased throughout the course of the winter. These images show the average daily ground surface temperatures at the same monthly compaction and undisturbed plots. The image on the left includes air temperature, while the image on the right includes 5 black lines, indicating when compaction took place. Until mid-January, temperatures remained fairly close, but after this period, they diverged significantly and maintained a difference of about 6 to 8 degrees. This may be due to the extreme temperature fluctuations that occurred early on in the study period, during the time when snow depth was at its lowest and the ground was least insulated. The higher thermal conductivity at the compacted plot means that its response was greater to both warming and cooling air temperatures, and early on those influences appear to have mitigated each other. Once air temperatures were consistently cold, then the ground surface temperatures diverged. When air temperatures warmed up again in the spring, the compacted plot also responded more quickly, reaching the zero curtain before the undisturbed plot, despite beginning at a much lower temperature. This was consistent with the response to temperature changes throughout the winter. The lag time was lower at the compacted plot, and this can be seen by comparing temperature peaks, which consistently came slightly earlier. It is also worth noting that due to COVID delays, compaction could not begin at the start of the winter. This may be critical for ground cooling, as it is when active layer freeze-up occurs. If compaction were to begin earlier, then the difference in ground temperatures between the plots may have been greater. These tables show the degree days, average temperature, and minimum temperature at all study plots, as well as the difference between the compacted and undisturbed plots. The temperature logger at the Stewart River site could not be recovered, while the logger at the Halfway Lakes plot was inoperable due to water damage. Ground temperatures were cooler at all compacted plots compared to the adjacent undisturbed plots. The greatest difference occurred at the plot which was compacted monthly, while the smallest was at the plot compacted only once. The difference between the monthly and bi-monthly plots was small, suggesting compaction may not need to occur frequently to have significant effects. The plot which was compacted early on in the winter was cooler than the plot which was compacted late, despite some unusually warm temperatures early in the study period. This may be because compaction early on exposes the ground to cold temperatures throughout the winter, while late compaction exposes the ground to warmer temperatures as the spring thaw approaches. Finally, I'd like to acknowledge some of the individuals and organizations who assisted with the project. First, I'd like to thank the Na-Cho Nyak First Nation for supporting the project and providing assistance with snow compaction and scouting field sites. I'd also like to thank Yukon Highways and Public Works for collaborating on the project and taking care of licensing. Jen Humphreys, whose experience in northern research was invaluable throughout the project, and Emily Stewart-Jones, who assisted with my final fieldwork trip in April. Fabrice Camels and Louis-Philippe Raw, who assisted with finding the Dempster Highway field site location, and Carleton University and PermafrostNet, who provided a strong network of support throughout the project. This concludes my presentation, and thank you for your time.